All right, so let's practice this one here with a man sitting in a canoe, and he's at rest in a still pond with the canoe there. And so let's call the canoe mass 2, the man mass 1, and we know that the man starts to move forward in the canoe at 0.5 meters per second, and we want to know what the canoe does. So yeah, see if you can use your equation sheet there and look at this relationship and figure out what's going on to figure out what happens to the canoe. And when you're ready to check, you can hit play to continue. Okay, so they're both starting from rest, and then so the initial velocities are 0, conservation momentum. Afterwards, the man moves forward 0.5. Want to find out what the canoe does. So the canoe is going to move backwards at negative 0.31 meters per second, and it's slightly slower than the man because there's a little bit more mass. And so if we start with 0 momentum, we should finish with 0 momentum. So if we place this right back in here, we'd end up getting 0 because the man moves forward, the canoe's got to move back for a momentum to be conserved. All right, let's try this one here with an air track, and mass 1 hits mass 2, and we want to find out first what the final velocity is of the 500-gram cart when it hits, and then we want to know if it's elastic or not. So remember the three collisions. Perfectly inelastic is where two objects hit, and then they stick together afterwards, and energy is lost. Elastic is where they hit and they bounce apart, and then energy is conserved. And then inelastic is when they hit and they bounce apart, but energy is not conserved. So yeah, go ahead and give this one a try here. Go ahead and calculate just the velocity first, and then we'll look at the energy part here in a second. So go ahead and do that. Pause the clip, and when you're ready to check, you can hit play to continue. Okay, so the final velocity of cart 1, negative 0.66 meters per second when it bounces back. And therefore, now we can look at the energy before and the energy afterwards to see if energy is conserved or not. Now, let's use the, it's 1.33 repeating value. So this is 0.66 repeating, or 2/3. And use those values as you do the energy before and energy after. And then we'll compare them. So go ahead and pause the clip and do that. When you're ready to check, you can hit play. All right, so beforehand we should get 1 joule, and then afterwards we also get 1 joule if we use the full values, 6.6 repeating, and then 1.33 repeating, 1 joule before, 1 joule after, so it is elastic. One of the things that's critical with circular motion is that the velocity is tangent, right? And then the acceleration is to the middle. And, you know, we work through that. If force is also to the middle, it's centripetal, like you trip and fall, centripetal force working towards the middle. All right, so in this one here, we've got a ball that's spinning, and we want to find out how fast it's spinning. We'll say that there's 42 newtons of force. The mass is 1.5 kilograms, and the radius is 0.25 meters. And so we want to find out, yeah, what is the speed at which it's spinning. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play. All right. So we can divide both sides by 1.5, and we get our, we can cross multiply 0.2 or 28 by 0.25, and then we take the square root. So it's going to be spinning at 2.65 meters per second as it goes around. All right, now in this one here, we're dealing with a car that's going on an on-ramp here onto 95, and we can look at what's going on. So let's say that the radius here is 40 meters as it goes around. The force of friction is 350 newtons, and the speed is what we want to find out. We know the mass is 1,800 kilograms. So yeah, go ahead and calculate the speed at which this car is going around. And then when you're ready to check, you can hit play. All right, so the centripetal force, mv squared over r, and we should get 2.79 meters per second for the speed of the car going around. All right, so let's try this one here. This is gravitation. What is the gravitational force between you and, assuming that you're 70 kilograms, and the Earth? And the distance between you and the Earth is 6,371 kilometers, which we need to get into meters. So yeah, see if you can use the gravitation equation and calculate the force of gravitation. And when you're ready to check, you can hit play to continue. Okay. So we've got our radius there. Make sure the radius is squared. I think on your equation sheet it's got d instead of r, representing distance instead of radius. Same thing. And we should get 686.977 newtons as the force of gravitation. All right, so one of the things that's interesting here when we look at gravitation and we look at a changing situation is if we're not given values, but we're given relative values. So we triple the distance between us and the desk, let's say. So between us and the center of the desk, this is distance, but then we triple it. You know, what's going to happen to the force of gravitation? So we want to look at the new over the old and determine what's going on. And so, you know, we set up G m1 m2 over 3 times the distance squared. And then the original situation is just distance squared. So, you know, the gravitational constant's the same, mass1's the same, mass2's the same. So we have 1 over 3 squared, d squared over 1 over d squared. And we can multiply the top and bottom by d squared. So it's going to be 1/9 as strong. And yeah, and that's good practice there. So let's now try, once you try this one, what happens if you half the distance between you and your desk? So go ahead and give this a try. And when you're ready to check, you can hit play to continue. Okay. So 1/2 r squared, and we've got our values cancel out. So it'll be 4 times as strong, right? So if you half the distance, it's a squared relationship, so it's going to be 4 times as strong. Now finally, with Kepler's laws, so we know that planets go in ellipses as they go around, and with the sun in one focus. And the second law is the planet sweeps out equal areas in equal times. And so, you know, when the sun, or when the Earth is closer to the sun, you know, we're moving around like this, and then, you know, we're carving out this area here, so this area is equal to this area. So when we're further away, we're moving slower, you know, from here to here, but we're carving out, again, the equal areas in equal times. And then finally, with the third law, we're dealing with, you know, the Earth here and maybe a satellite and another satellite, or the satellite and the moon way, way, way out there. So we're comparing the two around the same object, and then as it goes around, yeah, you know, we can compare the values there.